I don't know if that's, I thought,
yeah, so good morning, let's get started. Hello. Let's get started. So you should have the homework project. So all of module 1 basically graded so far, and I want to add something to the collaboration part, right? I think somebody asked me, what's the, if you just chatted, use your best judgment. If you just chatted and you got nothing out of it, you just said, I'm stuck in program, and somebody said, I'm also stuck. That's not considered collaboration, right? And obviously you don't have to code that you heard anything from me, because that's understood. But in general, if there is any possibility, err on the side of caution, right? And just to show you how important it is, like last year we had to let one graduate student go because there were some concerns on, there are two parties. One thought there was more collaboration than the other one, right? And long story, he had to be let go. So this is a very fairly serious stuff. So not just in this course, but anywhere, right? There is no penalty for you mentioning that you worked with any number of people within the class, outside the class, whatsoever. Because I hold you responsible for understanding what you did, right? I don't care where you got it, as long as you know what you did. So, but if you don't specify the name, then then the TA or me, when we grade it, we have to go through and figure out what really happened, right? So just to be on the safe side. So hopefully that answers it. And if you have any doubt, ask us or something before that. I didn't take any points in this one. I think the TA gave a warning for people who said we collaborated and not gave the names. They have no way of finding out people who collaborated but didn't say anything, right? So does that answer the collaboration part? So, yeah.
So the project says it's due Monday, February 24th, but Monday's the 27th, so is that going to be Monday?
I need to get a calendar. Whatever it says on the lecture thing is the correct one. I need to see what I think 24th is the right.
24th is the Friday before, Monday is the 27th.
So the last day of this module is when the project is due, right? And I have to see, I think 24th is the last day. If it is Friday, then it's a Friday. Right. So this is the grade so far, just for you to look at.
The syllabus says project 2 is due on Friday 24th.
Okay. Yeah, so it's Friday 24th. So it's always due on the last day of this module, right after the exams. So whenever that is. Right. So I sent an email out asking for feedback. So I set up a feedback form on SurveyMonkey. So if you have any comments about how the course is going, or in general, feel free to use that survey. It's anonymous. So, but if you want to talk to me about something non-anonymously, I'm always open, right? There's no penalty for that. So far in the first module we talked about processes and threads and stuff. So those are the mechanisms for you to assign a CPU, right? So in the subsequent modules, you'll notice that most of the modules talk about one component. You talk about memory management or storage management or what have you. For the CPU, one thing that we didn't touch upon, we kind of briefly mentioned when we talked about the pthread program, was when two threads share something, right, they cause problems. And this module is about what kind of problems they cause and how do you protect that. If two threads operate on the same data concurrently, then the results are undefined. Or the results can be any one of number of different possibilities. And most of the times you don't want that, right? You want your program to be predictable. You want your program to give you the one answer, right? Many of the times you have enough trouble making the program do what you want. You don't want it to do stuff on its own. So the goal here is to see what happens when you have multiple threads on sharing the same data and how you protect them, right? So the problem of this problem is critical section problem. So the notion is you have a section of code which is shared by a number of different threads. So you have to protect it from them manipulating them, and we'll look into locks and other mechanisms to how to protect this stuff, right? So that's the kind of the big picture of what we will do. So to illustrate what the problem is, and we saw that in the program we had before, but to make it more concrete, we'll go through a little code segment, right? Little segment of code and see what happens. So this is a producer-consumer problem, right? One is the producer is producing something and the consumer is taking something off the queue. So we start off with a count as 0, which means that there's nothing for the consumer to consume, right? When the producer produces something, it increments the counter. So you have one thread trying to increment it after it has some work, the other thread trying to decrement it, right? And if the count goes to 0, the consumer has to wait. And the count goes above the, so you can't let if it's a bounded buffer, the count cannot go above that, right? So the code segment would sort of look like this. I mean, obviously it's not the whole code. So basically you have the producer code and the consumer code. Producer goes in a loop and they both go in a loop. Right? And the producer looks to see if the buffer is full. If the buffer is full, it just waits there, right? And it produces some stuff magically using the next produced stuff, puts it into the buffer, and increments the counter, right? And the consumer goes to the same loop. If it sees something, it consumes it. So the relevant code that we're looking at is the count plus plus on the first code and count minus minus on the next code. That's data which is shared. Everything else is shared through the. So if you have the count right, then hopefully you can operate on buffer. That's shared too, and we'll have similar problems, right? So we will do a little bit of assembly language breakup of what that code looks like. So the count code in most operating system looks like. So have you looked at machine instructions and all in architecture course before? Right. So So if you haven't, you'll see it. You'll see a lot more of that in the future. So basically, it depends on what the particular architecture does. So the architectures have different notions of what they do and stuff. But typically, most operating system, most hardware expects the program to read the values into a register, do some arithmetic operations on it, and store it back. So a count plus plus would mean that the instruction would read the value for the counter from memory into register. It'll do the increment operation and it'll put it back on the memory location. And similarly for count 2, right? And if you took architecture courses, you'll notice that things can be a lot more complicated. Things can be rearranged and stuff. But for now, let's keep it as simple as you could, right? So if you start out with count equals 5, the outcome of this code depends on the interleaving that you end up with, right? So if you have them as 2 different threads running on 2 different processes, they can both run simultaneously. But to external observer, it can interleave in any number of ways. So for example, the first instruction from the first thread, and then the first instruction from the second thread, then the second one, it can interleave sort of like that. It can interleave where the first one completes, fully finishes, and then the second one goes. It can interleave where the first one does 2 instructions, and then it gets preempted, if you're talking about preempted kernel, and then the rest of the stuff happens, right? So there's multiple different ways in this the way it can happen. So one possible way of executing is given here, right? So basically the problem happens because there is a local register and there is a global variable, right? When register 1 makes a copy of it, right, things can happen underneath it and it's not aware of what's happening. So it can cache the value, you can basically read the counter value into its register, which means register 1 now happens to be 5, and it gets to increment the value, right? It goes to 6, and so at that instant, the second thread can read the contents off of the memory location, which still is 5. So it can read it. It'll cause it to go to 4, right? And then depending on who gets to win, right, you either get 4 or 6. So in the sequence we have register 1 went first. The producer went first, and then the consumer. So the end result is counter would be 4. If they had flipped, the counter would be 6, right? So in fact, you can actually have it go for the possible values are 4 or 5 or 6, right? If the so you'll get 5 if the increment happened fully and then the decrement happened, right? So depending on what sequence you have, this code can produce 4, 5, or 6, right? And it depends on either whether you have multiple processes or whether you have preemption, right? So do you think it's possible to have other values than 4, 5, and 6? So you kind of follow along how you get 4 and 5 and 6, right? So basically, if you follow the sequence, depending on whether the last two sentences are flipped, you get 4 or 6. Is it possible to get, say, a 3 with the same set of sequence? Yeah, I see only one response. No, right?
I would say no, because you only do one addition and one subtraction. Yes. So you could grade out 4 states.
Yes. So, yeah, you can't go below that stuff because there's only one subtraction and one addition. So, unless the instruction gets re-executed over and over again, in which case you can't really work with that machine, right? You can't go to 3 or other values, right? But any one of them are likely, and it depends on who wins the race. If you think of them both as running simultaneously, whoever wins, whoever is the last gets their value to stay, right? So that's why this problem is called a race condition. And race conditions are bad because it gives you unpredictable results, right? So what we're trying to do is figure out how to stop this from happening. So we introduce a notion of critical section, where you define critical section as the segment of your program where you're operating on shared variables, right? So the example we talked about before was fairly simple. It gets a lot more complicated, a lot more interesting when you have, when you have more like a transaction kind of behavior. We'll see it in the, in a few lectures. Basically, the idea is if you take money from your checking account and moving it to your savings account, right? You want these things to be protected, or else you can have. So in this case, 4 or 5 or 6 doesn't seem like a big deal, right? But if it's your checking account and instead of getting 6, if you get 4, right, you won't be happy. If it's the other way, the bank won't be happy, right? So it's a lot more significance when you talk about real stuff. In the toy example, it didn't seem like a big deal, right? So you define the notion of a critical section. So there's nothing magical about this code except you look at the program and say, this piece of code has to be treated specially. If you don't, if many threads start operating on this little piece of code, then you run into a problem, right? Then you also define a notion of an entry section and an exit section. Nothing like that actually exists in the program, but basically you say, before I go into the critical section, right, I have to do something to protect myself. After I get out of the critical section, I have to do something, right? And the rest of the code remains. So the rest of the code is not part of the critical section. They can do whatever they want, right? So this notion lets you figure out how to treat these sections differently. But if you look at an actual program, critical sections don't jump at you. So as a developer, it's up to you to make sure you recognize that there's sharing going on, and it's up to you to figure out if that sharing can cause problems, and protect it, right? And that's one of the hardest problems to deal with when you start writing multi-threaded code, right? The hardest part is to figure out what is a critical section, because that depends on your exact program, right? So for critical sections to be manageable and useful, you need 3 conditions to be satisfied. 3 requirements to be satisfied to have a useful notion of a critical section and what to do about them, right? And those are important. Those are stuff that we'll evaluate our algorithms by. So the first one is mutual exclusion, right? Which states that if you have a notion of critical section and you're trying to do something about it, right, only one thread can be running in it at any one time. If you have more than one thread running into it, then you notice what could go wrong. So the mutual exclusion principle says that when there are many threads or processors sharing the same stuff, if you implement critical section code properly in your entry and exit part, only one thread should be inside at any one time ever, right? If there's possibility of more than one thread inside the critical section, then you failed. Then you're not solving the critical section problem. The second principle is about progress, right? It's good to have notion of critical section. So you can solve critical section by saying no one can enter the critical section, right? That's also one solution, because that proves that the first part is true, except it's a horribly useless program, right? So the second stuff says you have to make progress, right? So you have to see some way that like one thread would yield to the next one, right? And more importantly, that decision should be made by the threads which are part of the critical section, right? And this is more for a fairness stuff. So if you have 4 threads in the process which could potentially be inside the critical section, only threads which are part of the critical section decide which one should go next, right? And the threads which are not part of the critical section can do whatever they want, but do not directly influence this decision, right? If you don't do that, then since the other code has no motivation to come back to the critical section, they can exit and stuff, and bad things can happen. Right? The last part is basically for a useful system. So you have to have a bounded weighting. So you don't want to precisely say that if you go to a critical section, if you ask for a critical section code, you'll get it back in an amount of time, in 4 seconds or what have you. But you have to be able to say that in certain amount of time, you have to be able to analyze it and say, after n trials, after some number of trials, you should be able to get through, right? So again, these last 2 are not necessary for correct functioning of the code, but if you don't enforce those, then your code, so some of the threads can starve because they don't get to run at all. So if you don't ensure these 2, then no one enters the critical section, or one thread keeps entering into the critical section, gets all its work done, the other one just starts, right? So, and again, we make no assumptions on how fast things are, how slow things are. We make no assumptions on real time. What we are assuming is how many rounds it goes before you get into the critical section, right? So these are the 3 requirements, and these are fairly obvious if you think about it, but they're used to evaluate if any solution that you come up with is truly a good solution, or if it only does part of it, right? If you write an entry section code which does not satisfy the first part, then it doesn't solve critical section problem at all. You have to ensure mutual exclusion, and to be good, you have to enforce other 2 options, right? So now we'll go to see how you can implement these critical sections, and we'll try to see how all of these policies are implemented by each one of them. Okay. So the first solution that we will look at is called the Peterson solution. It's a software-based solution, so it's interesting to look at it from that perspective, right? It assumes that load and store instruction cannot be interrupted, and which is not a valid assumption in most modern processors. So this section may not actually work on a real machine now, right? But it's a good way to see how you develop it, because that's what we'll translate into the next set of next method of solving this problem, right? Basically, it exposes how you come up with a solution, right? So it has a notion of two variables. There's a Boolean variable called flag, right, which has it concerns two processes or two threads. So the size of the flag array is 2, and turn indicates who should go, right? So and flag decides. Flag of I says whether process I is ready to go into the critical section, right? So if process I wants to go into the critical section, it should set the flag of I to 1, stating that it wants to get in, and turn says who can go, right? If the turn is me, and if I want to go in, I can go to the critical section. If the turn is you and I want to go, I have to wait, right? So here's the piece of code which would implement this, right? It will only be implementable if load and store cannot be interrupted. So assume that load and store cannot be interrupted, right? So what it does is, so for a process I, right, if it wants to get into the critical section, right, and the critical section is marked there, right? So first you have to set the flag of I to true, saying that I want to go into the critical section. Then I set the turn to J. J is the other process. So I don't set the turn to myself, I set the turn to the other process. And we'll see why that is important here, right? And so then you go into that little loop to see if, so you wait as long as it's the other process's turn and the other process wants to get in. So if the other process wants to get in, the flag of J will be true, and if it's the turn of the other process, then it gets to go, right? And when that becomes false, right, you go to the critical section, and when you're done, you set your flag to say you no longer need this critical section, right? So if two threads come in, right, it's not defined which one gets to go in first, right? The first thread which comes in would set the turn to the other one, right? So the other process will get to run. So after it finishes, it'll set its flag to false, which means that this equation will be false, right? So I get to run, right? So we can see why it solves these three principles: the notion of mutual exclusion, the notion of progress, and the notion of bounded wait, right? So the only way you can get in the critical section is if either it's the other person. So either it's my turn and the only way you can enter the critical section is if the other one does not want it, or it's my turn, right? So if that is the case and the other one won't enter, so you would still have mutual exclusion, right? So the reason why you implement progress in the wait is based on that turn equals J, right? Basically, when I'm done, I kind of pass the pattern to the other one, so the other thread gets to run, right? So I don't choose to run myself. I don't say turn equals I when I want to run. So when one thread finishes, if both threads are waiting, after one finishes, the next one has to run before control comes back to you, right? So unless the flag is so the turn equals J allows other process to run. So that's how you ensure progress, right? And you won't wait forever because when the other process finishes, you will get to go inside, right? So this piece of code will solve all the three attributes that we want, but it won't work on real machines because the interrupts can stop anything. So any of the assignments, so when you say turn equals J, those are not considered to be atomic. We'll see about that in a slide, right? So you can't guarantee that operation will happen in one shot, right? In real machines, that may involve loading registers and storing registers and stuff. So you can't ensure that each one of them can happen instantaneously. So for example, turn equals j cannot happen instantaneously. So if it doesn't, then bad things can happen. But this sort of code is what we develop for other stuff, right? And the way of like you having this flag, flag of j and turn of I, you basically go on a loop, right? And that's called busy waiting. So basically, one thread which does not have the lock is busy waiting because it's going in a very tight loop, right? The first while loop. So the process which does not have the CPU is going on a full CPU bound mode. It's basically checking and then going in a loop, which it would not be good from the scheduling perspective, right? You're going to be counted as a CPU bound job, and the CPU will try to throw you out and stuff. So it may or may not be good, and we'll see some cases where it's good and some cases where it's bad, right? So can you think of a case where this is good, where you're doing a busy loop?
Say if you have something that you want to execute as soon as possible, then you would want it to know that it's in the CPU, so to do that job.
Or if the critical section is very small, right? Yeah, if you really want to get in somewhere, the critical section you think is very small, then you don't care about wasting CPU, right? Is there another condition why this may be okay? Yeah, that's one excellent point. Yeah.
I feel like with the nuclear power plant problem, when something has to be accomplished before any other task.
Yeah. So that's an excellent point. So if you're doing real-time systems, right? If you're trying to do real-time systems, and if you're trying to do nuclear power plants and stuff, right? This kind of code is bad, right? In general. Because remember, if you're in a nuclear plant, you want everything to be absolutely predictable, right? If you're using critical sections and locks and stuff, I think 1 or 2 slides back I said, all you can guarantee is after I go through my critical section, I can give to you, right? I can only guarantee that, say, after 4 tries you get it, after 3 tries you get it, right? Usually that's not good enough for nuclear power plants kind of thing, right? They don't really care. They want to be able to say absolutely what time it happened. So if you use logs, right, you have to be extremely careful on how you do that, right? And that's an excellent point, but it's a very hard problem, right? Logs basically say that there are 2 threads which are coming around, right? I want one of them to go in, right? But if you're doing the nuclear power plant stuff, you don't want to say that. You want to say only this thread will have to go in, will do its stuff, and I don't care about what else happens, right? So it's a lot harder problem, but but if it's a softer real-time system, something like that may be solved, right? Yeah, we're not going to talk about real-time systems and how they solve it, and this is one of the areas where real-time systems will have to do something very complicated. So for the processing and stuff, I said, we can do O of 1 scheduler, which may be good enough for soft real-time and stuff. This kind of stuff, locking can't do. Right? Anyone wants to take a shot at the other case? You'll actually solve that for your homework assignment too, right? So the other case is multiple processors. If you have lots of processors, then you may not care about wasting the CPU as much, right? Which is sort of related to what you were saying. So if you expect the critical section to be small, and if you're on a multiprocessor, then you typically let it run. So because you don't really care about the so you're not as worried about the CPU. So you are willing to let them run for a little bit, right? But in a uniprocessor waiting like this is a disaster, right? Because if you're looping inside the loop, right? Unless there's some magic happen, unless there's an interrupt or something which interrupts and gives the other process, right? Even if the critical section is small and other process finishes, right? While you are going in the CPU loop, one cannot cannot run. There's only one processor, right? So you can try to keep it if you expect it to be interrupt-driven kind of mechanism, but for the most part, in a single processor, you don't have much choice. You're better off what is called yielding, right? You're better off at that point, say, if the condition is not true, I give up my CPU, and so I put myself on the wait queue, right? We'll see how you can do that later on. But basically, you have to do something like that. Otherwise, there's only one CPU, so you can't just busy wait. But it's an easy way for us to see what really happens, right? So it's very hard to implement this in software or machines where you don't have this atomic stuff, because the only way you can make these things happen is if you have absolute control over how the instruction that you're writing gets translated to machine code, right? And in typical programs, you don't have those niceties, right? So how many of you have some notion of what compilers do? It's actually a course you take in your 400 level.
Not a whole lot, but it's an overview.
So one of the things that I'm going to say it in a very high level, right? Your compiler course will go through this for a whole semester and more, right? So the idea is, if you want to write a simple code and translate it the way I talked about before, where I say I read something from a register and I write something into a register, so every line of code translates into a segment of assembly code, right? That will be an awfully slow program, awfully slow piece of code, right? No compiler worth its salt would do that, right? It won't even be acceptable as a course project for your compilers group, right? You want to optimize. So one of the steps that you try to optimize is you try to look beyond what you're looking to see what is actually in register. If count was actually in register, then you try to reuse it, right? Then you take it further and further. Then you see that you can try to use parallelism within the processor by moving instructions around, right? That's one of the things that you do, because if you say there are two instructions which have to happen, right? And I know that the processor itself is multi-threaded, has many units, arithmetic units and different units going through. Then I can move them around such that you won't notice a difference, right? Again, it depends on the processor and all those things, but that's why you optimize the compiler for a particular processor, right? So the code that you actually generate looks a lot different than what you wrote, right? And you want that for performance. So all the compilers, when you set the -O or any of the debugging options, they go really wild with the optimization, especially on a RISC processor, right? In fact, if you look at the assembly code, you can hardly tell how it came from. So in that world, you can't really implement locks using software, because if any of this stuff would throw away your assumptions. So what you really want is some sort of a support from the hardware, right? Some sort of support, some sort of instruction which the hardware guarantees will be atomic, meaning nothing would. So if you run this instruction, right, you'll either have the full stuff done or you'll have nothing done, right? You won't have partial results. So a complex instruction like incrementing a memory location, if the operating system was to do it atomically, it says if you start this instruction and it's done, you will only have it incremented. You don't have to have. So the piece of code I talked about before is not atomic, right? It has to happen 3 of those, right? So if the hardware says I can do count plus plus atomically, it has to do all 3 of them at once with no interleaving, right? And it cannot stop in the middle, right? So that's the notion of atomic instruction. So what we want is the hardware to provide some sort of atomic instructions, right? And see how we can use that to implement critical section code, right? And we'll see 2 different kinds of instruction that typical processors give you, and how we can use that to implement critical section, right? So one of them is a test and set. The other one is a swap, right? Swap says that if you give 2 memory locations, you swap the contents atomically, right? Meaning in one instruction, the values will be swapped. You don't have to worry about what happens. So, so basically, this is the algorithm which is done by the test and set on the top, right? So ignore the bottom code. So test and set basically says that if you give a location, right, it'll figure out, it'll test the value, it'll test what is in that location. Basically, it'll read what the content of the location, return it to you, and it'll set whatever, it'll set the value to true, right? So it'll read the contents of that location and then set it to true, all in one go, right? So basically, that's the piece of code that it's doing, right? Except it's implemented by the machine, so all of them happens all at once, right? So this is provided by the hardware. This is not a software thing. So you can't implement this in software and expect it to go. But if the hardware provides the notion of a test and set, that is the functionality, right? So next one is swap. So if you have two variables, you'll swap the values, right? So basically, the functionality is you'll copy it into a temporary variable. This is probably what you saw in C101 or something. So you copy it into a temporary variable, you swap the values, then you push it back, and you get out. Except the hardware guarantees that all of the operations happen all at once, all and at all, right? So when you're doing hardware, these instructions give you a lot of headache, right? So if you take hardware course, if you're designing any kind of processors, these instructions are a nightmare, right? So we are this is a software course, so we don't care about how they implement it, right? So they give you this instruction, so what we can do with that is what we focus on. So the first one is the test and set, and how we can use that to implement a critical section, right? This piece of code does not do the number 2 and 3 requirements. It does not implement the progress and the bounded weight condition, right? It only implements the mutual exclusion principle, and in one slide we'll see. Sorry, in 2 slides we'll see how we can add the stuff, and it makes it a little bit more complicated, right? So far, this is the piece of code. There are 2 threads, and so we have a variable called lock, right? And it's initialized to false in the beginning, right? If lock is false, that means that nobody has it. So the critical section, nobody is inside the critical section, right? So one of the threads. Each thread has the same piece of code. So the first thread comes in, and it'll do a test and set of the lock, right? And it loops on that variable. So it basically says that, so initially the lock was false, right? So when you do a test and set, right, variable lock is now set to true, and you are returned false, right? This test set returns what the value was. So you return the old value, which was false. So that means you succeed, and then you go on to the critical section, right? If at the same time another thread comes, right, it'll do a test and set. The lock is already true, so doing a test and set would still keep the lock as true, in which case you keep looping on that variable, right? When the first thread, which has the lock, finishes, it sets the value of false lock to false, right? And when it sets the value of lock to false, then the next test and set would return false and set the lock to true, right? So this way you guarantee that only one person can be inside the critical section. Does that make sense? So you may have to, this is one of those things that you may have to go back and think through and how these things happen, right? So there are two things which are trying to set. So the basic idea is, if a lock is already set, that means somebody is inside the critical section. So one which is not in the critical section will keep setting it back to true, but that's not harmful because we're not keeping track of who's having the lock. All you're keeping track is whether the lock is set or not, right? So the first one which comes in when lock was false would get to run because the old value would let it get out of the while loop, and by doing this instruction, it also sets the value to true, right? So does that make sense? And as we go to the next algorithms, some of them it's harder to go through them in the lecture. So I encourage you to go back and try to work through them to see what really happens, right? So next one is the using the swap, right? Swap basically says if you have two values, it'll swap the thing. So with the using the swap instruction, right? So this is the piece of code. Again, it does not do the second two stuff that we talked about. It only implements the mutual exclusion policy. So basically now you have a global variable called lock and a local variable called key, right? The local variable is local to each thread, and the global variable is, of course, global, right? So when the code comes through, right, the first thread sets key to true, right, and he'll do a swap, right? So when you start out, lock has to be false. So nobody is inside the critical section, so lock is false. So you go in a loop as long as key is true, and key is being swapped with what the conditions of the lock is, right? So if the value of the lock was false, the first time you get through, you will swap it, right? Which makes the lock to be true, right? And key to be false. When key is false, you fall out of the loop, right? But otherwise, if the key is true and lock, so the next thread which comes through, key is true, lock is true. So you can keep swapping, but they are the same value. So the key will always be true. So it'll be looping on that instruction. So when the first thread sets the lock to be false, then the swap will succeed. Right? Does that make sense? So again, this only works if swap is atomic. If swap can be stopped in the middle, if anything can swap in the middle of the swap, then this would not happen. But if a machine provides a hardware way of doing swap atomically, then doing this piece of code would ensure that only one thread can be inside the critical section. Right? These are two different ways of implementing critical section using test and set or swap instruction. And these are both hardware-based solutions. Right? So I have one more example here. I'll try to go through them in class, but more likely you would have to go through them by yourself at your leisure, right? So basically now you're taking the test and set solution and you're trying to make it to be bounded weight, right? So you want to guarantee that the other thread will get it after a certain number of tries. So you don't want to say it. So in the first case, if you're lucky, right, you keep going back into the loop, and if you keep getting the right set of sequence, then you can be lucky forever, right? But in this piece of code, that would not happen. The way you enforce that is you basically have, if the piece of code at the bottom here in the high level, j equals I plus 1 %n. Basically, if you have a number of processes, right, when I'm finished, right, I basically try to see if there's anybody else in the queue waiting. So there's now a array called waiting, which shows the number of threads which are waiting, right? So when I finish with the critical section, right, I try to see if anybody else is waiting from me. I loop through, right? So I say j equals I plus 1. So I got the lock right now. So I'm going to look at the next thread, right, and see if that is waiting, right? If it is waiting, I wake that up, right? If it's not waiting, I try the next one. I go in a loop and try the next one. If no one else is waiting and it comes back to me, that means nobody else wants the lock, so I set the lock to false, right? If anybody else is on the list, then I set the waiting for that to false. That means he'll get to run. Lock still remains true, so nobody else can come in, right? So what I'm really doing is when I'm finished, I'm trying to see who else is around in a orderly fashion. I'm trying to see in a ring kind of fashion, right? So I'm trying to see if there's anybody waiting. If they are waiting, then I give the lock to them, and when they are finished, they give it to them, kind of stuff. So if all the processes are waiting, you wait at most n time, right? At most a number of processes. Because when I'm done, I can't take it back. I have to give the log back to the next person, and they have to give to the next person, and so on, right? So this ensures that you can bound the amount of wait. You can say after if there are n processes, at most you'll wait for n different threads to keep the lock before I can get it back. It makes no guarantees on how much time it will take because that depends on the critical section code, right? Whatever happens in there. But it says that if all of them are waiting, I know precisely how many turns I have to wait till I get the stuff. Not good enough for real time, but good enough for normal programs, right? So hopefully this piece of code it's obvious. It's basically mixes some of the stuff we looked from the Peterson's algorithms and so on. But that's what is happening. You're trying to see who's next in the queue, and you're kind of handing it off to them without ever resetting the lock so that somebody else can take it. Right now, it's an orderly fashion of who gets to go. Right. So that's about it for today. These are important things, and your homework assignment goes through many of this stuff, and we'll stay with this for a while. So I'll see you on Friday.